right, guys, what I want to look at today is actually section 4.4 from your book, but it's referred to as conditional probability, and then there's a second part that deals with independence. But here's the first situation I want you to think about. If you were going to toss a fair coin twice, what's the probability that you got two tails when you flip the coin twice? So let's kind of think through this here. So I know I flipped that first coin and I got a couple options. I could have gotten heads the first time, and I could have gotten tails the first time. Let's say I got heads the first time. Well, if I flip it again, I could have gotten heads again. Or maybe I got heads the first time and I followed that up with a tail. The other option could have been I got tails first time and then I got heads. Or maybe I got two tails in a row. Well, the question is, well, what's the probability that we got two tails? Well, that only happened one time out of those four options. So I'd say the probability of getting two tails was 1/4. Well, what if this situation changes slightly? What if I said this? If I toss the first one and it lands on heads, what's the probability of getting two tails? So I'm saying, okay, I tossed the first and I got heads, which would be one of these two situations. What's the probability of getting two tails? Well, of those two situations, none of those had two tails. So things changed when I knew what happened on the first coin flip. Or knowing the first result changes the probability that I got two tails. That idea of knowing a result already and having that result affect my probability is the basis of conditional probability. So the probability that one event happens, given that another event is known to have happened, that's what's referred to as a conditional probability. There was a condition on it, okay? The probability if this already happened. Well, notation for that. If I were looking at a situation where I have a conditional probability that event B happens, given that event A has already happened, we're going to write that like this. The probability that B happens, given that, that's going to be a straight up and down vertical line, A has already happened. All right, how are we going to use it? Well, I'm going to go back to that example that we did the other day, the one where they did the survey, they kept track of males and females, asked them, did they want to be happy, healthy, rich, or famous? And we're going to define events as F being selecting a female, H being someone who is happy, R being someone or somebody that wanted to be happy, and then R would be someone who wanted to be rich. Well, here's the first one that they're asking. They want to know what's the probability that I selected someone who wanted to be happy, given that they were a female. Okay, so this one we know. Well, the nice thing about that is as soon as I know it's a female, that's the only data I'm going to look at. In other words, in this table here, since I know I'm only looking at a female, that's the only data I'm going to worry about. So I go to that data and I look for the number that answered happy. Well, that was 90. I only focused on the females, so there were 120 females. So the probability, if I were to go ahead and divide it, would be 0.75 or 75%. So it's kind of nice because if I know the situation already, well, that's all I have to focus on. All right, here's the next one. Now, there's some notation on this that I need to talk about before we actually answer the question, but here's the question that they give me. Given that the chosen person did not choose to be rich, what's the probability that this person is female? So again, what we know is this part. Now, you'll notice it has an R with a little c there. That little c is really talking about the complement of R. And we've talked about complements before. That's the not portion. In this case, the ones that did not answer that they wanted to be rich. So let's go to our table again here. Again, the question wants to know what's the probability that we chose the female given that the person did not want to be rich. Well, as soon as I hear that they did not want to be rich, that eliminates all these people that said they did want to be rich. So they're now out of the picture. Well, let's see of the ones that were left. First of all, how many were female? Well, we used to have 120 females, but we're throwing out all those females that said they wanted to be rich. So now instead of 120, I'm down to 110. That's out of all the people we talked to, which originally was 218, but we're taking out 41 of them. So that gets me down to 177. And again, if I punch that in, divided it out, I'd find out this is 0.62. So by knowing that they did not answer rich, that eliminates all those questions, or all those answers, I should say. And it narrows down the data that I would focus on. Well, we can do conditional probabilities with Venn diagrams as well. Now, I'm going to show you some things the book uses for formulas, but they get a little bit confusing. Here's really what I would suggest doing and what I would suggest focusing on. It's just this first part. So it says, what's the probability that A happens given that B happened? Well, the way I can figure that out is I can figure out, well, what's the probability that A and B happen, so both of them happen, divided by the probability of just the given fact, or B, happening. These are just other ways to write it, but I wouldn't worry about these things. I just wanted to show those to you because the book sometimes puts those in there. So how are we going to figure this out? Well, here's my Venn diagram. This is an example where we're looking at people that owned a dog, people that owned a cat, and it also represents the probability that they own both of those. So here's what we want to try to figure out. We want to know what's the probability that a randomly selected resident, that we would select a random resident who owns a cat also owns a dog. Okay, so what's the probability that a randomly selected resident who owns a cat also owns a dog? So we want to know, okay, what's the probability that they own a dog given that they own a cat? Because we said right here, who owns a cat. That's something we knew. Well, we can figure this out by looking at what's the probability of both happening divided by what's the probability of the given fact happening. So I go to my Venn diagram. Well, the probability of both of those happening is the overlap. That's the 0.18. the probability of owning a cat is anything in this cat circle. Well, that's two parts, 0.18 and 0.14. So I put those two things together and I get 0.32. And so I type that in, I see what 0.18 divided by 0.32 is, and I find out the probability is 56% or 0.56. So when we look at a situation with Venn diagrams, that formula, I think, is the best way to attack it. So conditional probability, knowing something happened already, what's the probability now that something else is going to happen? Well, conditional probability actually helps us make a decision related to what's called independence. So let's say that I called event A as tossing a coin and it coming up heads. Event B is tossing the second time and it comes up heads again. Here's what I want to know. What's the probability of B happening? In other words, I get heads on the second toss, given that A happened. Or in other words, I got heads on the first toss. So this I know. I want to know then what's the probability that I get heads the second time. Well, let's think about it. If I get heads the first time, and then I start over. Well, as soon as I start over, the probability of getting heads is 1/2. Because when I flip the coin again, it's still either heads or tails. What about this? What's the probability that I end up getting heads on the second toss, given that I did not get heads on the first one? Or in other words, the first time I got tails, what's the probability that I get heads the second time? Well, again, as soon as I start over, I flip the coin, I got tails. All right, big deal. I'm getting ready to flip it again. Well, the probability of getting heads is still 1 out of 2. So when this happens, the fact that the probability of B happening when I knew A happened, since it equals 1/2, and the probability of B happening when A did not happen, since those two were equal, they also actually just matched what the probability of B happening was in the first place. In other words, knowing what happened first did not change the probability of that second toss. Well, because the probability was not changed, I'm going to say that A and B are independent events. And independent events, or I can label them as independent events, if knowing whether or not one event has happened does not change the probability that the other will happen. If you think about it, I have independence, well, I'm free from other things. Let's check and see if we have independence in certain situations. Well, again, a lot of notation here, and don't get caught up in the notation. Again, I'm just showing you this because the book sometimes shows those different ways of writing it. But basically what we're saying is I should be able to go either direction and get the same probability. I think it's probably easier if we just look at an example. So here's our example. We've got data on gender and allergies. and they're from a random sample of 227 students. So they were responsible for this online survey at Census at School website. So they looked at males, females, whether they had allergies, whether they did not have allergies. All right, so suppose we chose one of the students from the sample, and we're looking at the events of choosing a female and the event that they have allergies. We want to know, are these two things independent of one another? Well, if they're independent, the probability that they have allergies, given that they're female, should be the same as them having allergies, given that they're not female. So let's start out with the first part. So I want to know, what's the probability that they have allergies, given that they are a female? Well, since I know that they're a female, I'm going to focus only on the female data. Well, in that female data, we have 50 that had allergies out of 130 females that we talked to. So if I take 50 divided by 130, I get 0.38. So the probability that they have allergies, given that they are a female, is roughly 38%. Now we're going to compare that to the probability that they have allergies, given that they are not female. So now I'm going to focus only on the male data. When we looked at the males, we had 34 with allergies out of 97 males. So I punch that in. And when I punch that in, I get 0.35. Well, if I do a comparison here and I ask myself, okay, is it more likely that a female has allergies? Is it more likely that a male has allergies? Or are they the same? If they're the same, I would say that they were independent, because we're saying it doesn't matter whether you're a female or a male, the probability of having allergies is the same. Well, in this case, they're not the same. So that tells me that they are not independent. In other words, based on this data, it's more likely that someone has allergies if they are a female versus having allergies if they're a male. So to me, this is one of the tougher sections. Again, don't overly stress yourself. I know this is a difficult situation since we're not together, but I do want you to get an idea of some things that you might see later on in terms of probability. So for right now, I want you to kind of practice conditional probabilities, and then also try to decide whether we have independent situations.